Hi, Year 11, and welcome to our very first lesson for advanced mathematics. Our first topic is arithmetic and algebra, and this is the first in a series of 5 videos for this topic. In this first video, we're going to look at arithmetic. Now, most of this you've learnt before, but I just want to go through it because there might be some gaps in your knowledge, and then you can do a little bit of work just to catch up. We're going to look at real numbers, rational numbers, reciprocals, significant figures, scientific notation, absolute value and exact value. All real numbers can be represented on a real number line, and you would be familiar with all of these types of numbers, but maybe what you don't know are these symbols. So this is the set of all real numbers and has the symbol R. It's a funny looking R, but when I write it, I just tend to do 2 lines like this and then the rest of the R. Inside the set of real numbers, we have the rational numbers. We're going to look at those shortly. It has the symbol Q. And we have the irrational numbers. And we write Q with an apostrophe next to it. That means not rational. Inside the rational numbers, we have the integers. They're the negative whole numbers and the positive numbers and 0. And inside the set of integers, we have the natural numbers n, which is the counting numbers. So 1, 2, 3, 4, etc. A rational number can be expressed in the form a over b, where b is not equal to 0 and a and b are both integers. And we've got various types of numbers that fit into this category. So for example, integers can be written in the form a over b. If we got the integer 4, for example, we could write that as 4 over 1. So it's a rational number. Fractions obviously are rational because they're already written in that form. Terminating decimals, so 0.2, that's the same as 2 over 10 or 1/5. So it's written in the form a over b. Percentages, 25%, that's a quarter. And also recurring decimals. So 0.3 repeater, that's actually equal to 1/3. There are 2 acceptable notations for recurring decimals, and you can use either one. So we can either put a dot over the top of the repeating digit or a line over the top of the repeating digit. And we say 0.3 repeater. And this is the same as 0.333333, etc., etc. If we've got 2 repeating digits, we put a dot over the top of both of them, or the line straight over the top. And this is the same as 0.414141, etc. If we have more than 2 repeating digits, we just dot the first and the last digit that repeats. But if you use this sort of notation, we put a line all the way over the top of it. And this is the same as 0.20932093, etc. Every recurring decimal can be expressed as a fraction, and we saw that before with 0.3 repeater being written as 1/3. But what about something that we're not familiar with, like 0.4 repeater? We use an algorithm to show how this can be expressed as a fraction. We start off by saying let's let x equal 0.4 repeater. And I'm going to multiply both sides of this equation by 10. Now have a think about this. This is equal to 0.444444, etc. So when I multiply by 10, I'm moving my decimal place 1 position. So I'm going to get 10x is equal to 4.4 repeater. Okay, because this goes off to infinity. So moving the decimal point 1 position isn't going to change that part. Hopefully that makes sense to you. Now what I'm going to do is subtract this one here from this. So I'm going to go 10x take away x, which is 9x, and 4.4 repeater take away 0.4 repeater. And that's going to get rid of my repeating bit. So I'm going to end up with 9x is equal to 4. So just pause for a minute and make sure that makes sense while we get rid of these parts here. It's easy from here. We divide both sides by 9 and x is equal to 4/9. So if you put that in your calculator, 4 divided by 9 and turn it into a decimal, you will actually get 0.444444, etc. Okay, here's another example. Express 0.35 repeater as a fraction. So again, I'm going to start with let x equal 0.35 repeater, but this time I'm going to multiply by 100. It's going to give me 100x is equal to, and what's this going to be? Let's just write it out a bit. It's 0.3535, etc. When I move the decimal place 2 positions, I'm going to get 35.35 repeater. Does that make sense? Again, subtract, so 100x take away x is 99x. 35.35 repeater take away 0.35 repeater. These parts here will be subtracted. Is going to equal 35. Divide both sides by 99, and x is equal to 35 on 99. Now here's the main rule. However many digits are repeating, we multiply both sides by 10 to the power of that number. So in this case there's 2, so I want to multiply it by 10 squared, which is 100. Okay, one more. This one's a bit trickier because you can see I've got a 0 here that's not going to repeat. So this is the same as 0.031313131, etc. And it's going to cause a bit of grief. I'm still going to start the same way. Let x equal 0.0 and then the repeating part 31. Now what are we going to do here? We want to multiply by 100, but that's not going to help me because when I move my decimal place across here, I'm going to end up in between. It's going to end up in between the 3 and the 1. So I'm actually going to do something sneaky to start with. I'm going to multiply by 10 so that I get back to the same sort of questions that we were just doing. Okay, I've got rid of that 0. Now I have 2 repeating digits, so I want to multiply both sides by 100. So 10 times 100 gives me 1,000. And here I'm moving my decimal place 2 positions, 31.31 repeater. Subtract. 1,000x take away 10x is 990x. 31.31 repeater take away 0.31 repeater is 31. Divide both sides by 990. 31 on 990. Okay, let's move on. The reciprocal of a number x is 1 on x or x to the power of -1. So if we want to write the reciprocal of 2/3, we could write it as 1 over 2/3, or we could just turn it upside down because 1 divided by 2/3 is the same as 1 multiplied by 3/2. Okay, so there's the reciprocal. Just flip it upside down. If we want to write the reciprocal of a mixed numeral, we have to turn it to an improper fraction first of all. 3 3s and 9 plus 1 is 10. So as an improper fraction, it is 10 over 3. And then the reciprocal, turned upside down, is 3 over 10. On your calculator, there's this button here, x to the -1, and it will do the reciprocals for you. What do you think is the reciprocal of 0? Well, that's 1 over 0, or 1 divided by 0, isn't it? What's the rule here? Anything divided by 0 tends towards infinity. We don't say equals infinity because we can never get there. We use this arrow. Now, do you know why this is? This means how many zeros go into 1. And no matter how many times I try and put 0 into 1, I'm never going to fill it up. Think about a 1-litre container and you are pouring in an empty bottle. You can keep doing that until infinity and you're never going to fill that container. So the reciprocal of 0 tends towards infinity. Now, a significant figure is a digit other than 0 unless the 0 is in between 2 other significant figures. So for example, 0.003 has one significant figure. It's the 3. And all of the non-significant figures, the zeros, are just place value holders. In fact, all they're doing is pushing this 3 out into the thousandths position. But this number here has 4 significant figures because these zeros are in between 2 other significant figures. Now, occasionally you might be asked to round an answer to a certain number of significant figures, and we follow the normal rules for rounding. So in this case, we want to keep the 3, the 5, and the 6, but we want to throw away this 8 and 9. But it's too big to throw away because that 8 is greater than or equal to 5, so we're going to round up. So this is approximately equal to 0.00357. We might have a large number, so we've got 120,990. We want to keep the 1, the 2, and this digit here. Look at the next bit, too big. We're going to round up. So this is approximately equal to 121,000. And then finally this one. Sometimes they won't always work out. Have a look at this. We want to keep the 1, the 3, and this digit. But no amount of rounding here is going to make that anything other than 0. So in fact, we're going to write that as 13,000. And it looks like it only has 2 significant figures, but we actually have rounded it to 3. Scientific notation is a method of approximating very large or very small numbers. And what it does is eliminate all the insignificant zeros. So if we want to write 2,160,000 in scientific notation, we're going to move our decimal point from here to after the first significant figure. So it's going to become 2.16. We're going to then multiply by 10, and we're going to count the number of positions we've moved the decimal place. So it is 1, 2, 3, 4, 5, 6, and that's going to be our power. So there's scientific notation for this number. We can also do it with small numbers. Again, move the decimal point to after the first significant figure, so 2.3. We're going to multiply by 10, but this time it's going to be a negative power, and we're moving how many positions? 1, 2, 3, 4, 5, so it's going to be negative 5. And here's the rule. The power is positive for large numbers like this one, and negative for small numbers, and you might actually know why that is. If we want to expand the numbers, then we take our number 3.14 times 10 to the power of 5. This one's a large number, so I'm going to put the 314 at the front, and I'm going to move that decimal point 5 positions. So 1, 2, 3, 4, 5. And I'm going to fill in zeros underneath. So we have 314,000. And we can also do it with small numbers, 3.14 times 10 to the power of negative 5. So this time I'm going to put this 314 down here on the right hand side. I'm moving the decimal point 5 positions to the left this time, and fill in underneath with zeros. We've got 0.0000314. Now on your calculator, you can enter scientific notation by using this button. It's actually a good idea. It gets around order of operations problems. So anytime you've got scientific notation, try and remember to use that button rather than times 10 to the power of. A reminder that a directed number has both size and direction, and you learnt this in Year 7. For example, positive 8 is different to negative 8, but the absolute value of a number is the size of the number without the direction. So this is what we write. These are the absolute value signs. The absolute value of positive 5 is equal to the absolute value of negative 5, and it's just 5. If you get a question like this, we treat these like brackets, so we work out inside first. So negative 3 plus 2 is negative 1, take away 6 is negative 7, and then do the absolute value. Absolute value of negative 7 is just 7. Okay, finally, we talked about rational numbers before, and they can be written in the form a over b, where a and b are integers and b is not equal to 0. But an irrational number, and remember that was the symbol q with the apostrophe next to it, it's a non-terminating, non-recurring decimal, and it cannot be expressed as a fraction. Now, arguably the most famous irrational number is pi, and I'm sure you're familiar with it, but there are others. There's e, the natural number, and we're going to meet that later on in Year 11. But there's also surds, like the square root of 2 and square root of 5. Okay, let's look at this example. Complete the following table. We have various types of numbers, and we want to say whether these numbers belong to these sets or not. So remember, we have real numbers, rational numbers, irrational numbers, integers, positive integers, and natural numbers. Okay, first one, negative 7. It is a real number. It is a rational number because we can write it as a fraction. It's not irrational. It is an integer. It's not a positive integer, and it's not a natural number. Get the idea? Here we have a decimal, a terminating decimal. It is real, it is rational, it's not irrational, and it's not an integer. 5 over 2, it is real, it is rational, it's not irrational, it's not an integer, it's not a natural number. Square root of 3, okay, it is real, but it's not rational, so it's irrational. Does that make sense? And then it's not going to be an integer or a natural number. Square root of 9, trick question. That's 3, isn't it? So it's real and rational. It's not irrational. It is an integer. It is a positive integer. And it is a natural number because it's 3. And then finally we have a recurring decimal. It's real. It's rational. It's not irrational. It's not an integer. Make sense? Hope so. Okay, last thing, I promise. Often in maths we'll be asked to leave our answer in exact form, and this means as a surd or a fraction or a repeating decimal, but not as a truncated decimal. So like a number that you've rounded to 2 decimal places or 3 significant figures. So the following are in exact form, and then we've got some approximations shown next to them. So for example, the square root of 3 is approximately equal to 1.732. So I've truncated this, I've rounded it. This is the exact form, this is the approximate form. Pi is approximately equal to 3.14159, approximate form, exact form. 2/3, we could write that as 0.6 repeated, that's exact form, or it's approximately equal to 0.666. Here I have truncated it. So this is the approximate form, and these ones here are the exact form. I want to show you this one. What do you think about this? We know that pi is equal to 22/7, don't we? You might have heard that. It's not actually equal to 22/7 because pi is an irrational number and it can't be written as a fraction. This is an approximation. So this is the exact form here, and this is the approximate form. Okay, that's it. Our next lesson is on algebra.